Arvind Ayyer. He will speak about interacting particle systems and symmetric functions.
Okay, thank you for the kind invitation and the introduction. And I wish Ron and Yuval many happy returns on their 60th birthdays. So I want to talk about some joint work with a bunch of collaborators, which I'll mention later. I want to mainly advertise the area of interacting particle systems to the audience. I think this has somehow escaped the attention of many people in this community. And I think there are a lot of interesting problems, and I want to sort of advertise this. So here's the outline of my talk. I'll first give a brief overview of interacting particle systems, give some examples. And I want to spend most of my time on this new model, which I call the MTALREP, or multi-species totally asymmetric long-range exclusion process, for which we are able to say a lot using combinatorial techniques and probabilistic techniques. And then I want to give a refined version of that, which I will explain is related to McDonald polynomials. And if I have time, which I very much doubt, I will say something about this multi-species totally asymmetric zero-range process, which are related to the modified McDonald polynomials. Okay, so let's start with interacting particle systems. And I should say I'm on a Linux machine, and Zoom has not been optimized for Linux, so I cannot see your questions. So please feel free to interrupt me at any time. Or the moderators or the chair, Piotr, can interrupt me if anything is not clear. Okay, so interacting particle systems in the probability literature or lattice gases in the physics literature, they're basically stochastic processes on graphs, and this could be understood at, and this could be studied at various levels. For us, we will think of interacting random walks and therefore Markow processes. And so at every graph, you are going to have vertices and edges, of course, and at every vertex, you'll have a number of particles of possibly different species and possibly no particle as well. And each particle will move to one of its neighbors with a certain probability when you're thinking of a discrete Markov process, or with a certain rate for continuous Markov process. And this movement will depend on the environment. So in other words, it depends in principle on the configuration of particles in the rest of the graph. And particles can also be born or die stochastically at certain vertices. So this is the rough setting. And why should you care? So as I said, these are important in probability and statistical physics. And they're also of increasing interest to algebraists working in representation theory and these people who can be integrated. So, and for in many cases, they are interested in models with disorder. So that means you have certain parameters which you want to choose from some probability distribution. But for us, we will think of disorder as parameters which will be symbolic variables, which as is common in combinatorics. And so the aim is that if we have a combinatorial understanding, we can hope to calculate quantities of interest. And what are the quantities? I mean, for example, physicists and probabilists are interested in things like currents, correlations, mixing times, large deviation functions, and so on. So if you don't know any of these terms, it's okay. I mean, I'm not going to talk about any of these. I'm just trying to say why one could do a lot. So let me give you some examples before we go ahead. So exclusion process is something that may be most familiar to this audience. Here, every site contains one or no particle, and each particle moves to one of its neighbors provided the target is vacant. So the only interaction is exclusion. So no more than one site, no more than one particle can be at a site. Another class of processes are the zero range processes. So here, every site can contain an arbitrary number of particles. And so if you imagine there's a tower of particles sitting at a site, and then what happens is that with a rate depending solely on the number of particles at that site, a particle will move to one of its neighbors. So it's called zero range because the range of the interaction is zero in the sense that it only depends on the origin site. So contact process is another example. So each site here is either infected or healthy. Again, you can think of this as 0, 1. And healthy sites get sick at a rate proportional to the number of infected neighbors. And healthy site and infected neighbors recover at rate map. So this is probably a model that is of current interest, although it's much older. So the voter model is where every site is a voter, it's a population, and you have a friendship graph or something, and there are two candidates in an election, and everybody has an opinion, and each voter chooses a random neighbor and takes on their opinion. So that's an example of another interactive model. There are of course many others, and surprisingly, most of these models were proposed in a single paper by Frank Spitzer in the advances in 1970. It's rather remarkable. So he set this whole field going with just this one paper. There, of course, that was for the probabilistic audience, and but we want to think more in the combinatorial setting. So for us, we will only restrict to finite graphs, and in particular, we'll focus either on path graphs, which are one-dimensional graphs with, so Pn stands for the path graph with n vertices, or Cn is the cycle graph with n vertices where you have them arranged in a ring. And we'll only work with finite number of particles, so we have a finite state Markov chain. And we will only work in continuous time, although I will give some discrete time example as well. So there is an underlying generator, or what physicists call the Markov matrix. This so everything comes out from this matrix. So the matrix is as follows. So its off-diagonal entry, so omega omega prime with entry, is the rate from omega prime to omega. So this is somewhat different from the probabilist convention. This is more the physics convention. This is column stochastic. So this is not the rate of omega to omega. And on the diagonal entry is such that the column sums are 0. So this is why it's called the column stochastic. And just to remind you, a Markov process is called irreducible if you can get from any state to any other state in the configuration space using a series of legal transitions. So we will only work with irreducible finite state Markov chains in continuous time. So that is the setting. So I should say, this is an aside, but there is increasing interest in interacting particle systems, mainly on Z, where symmetric functions also play a role. I mean, you might have heard of Schur processes and the Schur process and the McDonald process. So here the Schur polynomials and the McDonald polynomials play a role. But, these are some people who have worked on this, and they have interesting connections to representation theory, but I will not focus on this side of this discussion. Okay, so we are going to be interested in the stationary distribution. So what the stationary distribution for an irreducible process is what happens after a long time. So you run the process, you wait for some time, and then you look at the system, and it has a probability distribution given by what is called the stationary distribution. And remember, we have this Markov matrix M. And so if the process is irreducible, there is a unique right vector, that is column vector, V, which determines the stationary distribution. So by the Frobenius theorem, all entries in V are positive. Well, what does that mean? So if your matrix has is a purely numerical matrix, this makes sense. So then these are positive real numbers. But if you have parameters, what does this mean? So I'll explain that in the next slide. But assume that this makes sense, then the stationary, we'll call the stationary weight of configuration V of omega. And the stationary probability will be pi of omega, which is V of omega by Z, and Z is the partition function. It's just the sum over the V omegas. I did not write it, but yeah, that's what it is because it's a probability. And this is called the partition function with some abuse of terminology, because for physicists, partition function is a loaded term. It carries a lot of meaning. But we have gotten into the habit of using this term. You can see this is slightly problematic because, I could multiply V of omega by 2 for every omega, and then my Z will multiply by 2 as well. So a priori, this is not well defined. So a common theme in the combinatorial setting is to give combinatorial interpretations of this V omega and partition function. Okay. So here is a really beautiful theorem which somehow has not been so widely appreciated. So I want to advertise this. So suppose you have, so we'll take the most general Markov chain on n vertices. Okay. So the ijth and the transition rate from state I to state j.
Excuse me.
Yes.
You talked earlier about graphs, but it's not clear to me that the graphs, the edges, are playing any role in what you're describing.
No. The edges have weights. So this you think of as the weight of the edge.
If you can go from any I to any j, then the graph is the full graph on n vertices.
So in this setting, it's the complete graph.
So it's not the path or the cycle, it's the full graph.
Yes. So right. For this example, yes. For this theorem, yeah. But since these xij's are arbitrary, you can set some of them to 0 or most of them to 0. But that's right. So so in this example section over here, I will work only on paths and cycles. But this is a very general theorem, which I think it's good to know. So you have this Markov chain, this most general Markov chain. Xij's are completely symbolic variables. We don't give them any numerical values. And to describe the stationary distribution, I recall that an arborescence is a directed rooted tree where all edges are pointing away from the root. So, I mean, there are conventions, but this is the convention I will use. So you have a tree. So you take a tree and you direct, sorry, let me start again. You have a tree, you have a root, and you direct all edges away from the root to get an arborescence. So let Aj be the set of all arborescences on n vertices with J as the root.
You're not requiring that they be spanning trees, any tree whatsoever?
Yeah, this is the complete graph. So any tree is a spanning tree.
I don't understand. A tree could be, some small subset of vertices. You're not requiring that the tree span the graph?
No, tree spans the graph.
Okay.
On n, yeah.
Spanning trees, okay.
Yeah. Right. So Aj is the set of all arborescences with J as the root. And if you have an edge A to B in your arborescence, you give it weight XAB, the same X over there. And the weight of an arborescence is going to be the product of all the edge weights. Okay. So here is this beautiful theorem by, it's called the Markov chain tree theorem as a riff on the matrix tree theorem. This was proven by Layton and Revest. Revest is the famous Ron Revest of RSA, and I think his co-author Shamir has an Israel connection, but I think Revest is at MIT. But this was known to Terrell Hill as a physicist in the 60s as well, but without, I don't think he wrote down a formal proof. So the stationary weight of this very general Markov chain, the most general Markov chain, in fact, is a sum over all arborescence, weighted sum over arborescences in with J as the root. Okay. So what this says is that you have n to the n minus 2 terms for each J, because every tree will appear as an arborescence for in AJ. It's just that the direction will change. And the sum, therefore, will have n to the n minus 1 monoid. So you can see why it's called the Markov chain tree. Okay, so that's the partition function. So the point of this is that V is now a positive sum of, I mean, it's a polynomial in the rates with integer coefficients and non-negative, with non-negative integer coefficients. Okay. So that's what it means for this when I said V is positive, the entries in V are positive. Okay. So let's go to a toy example. So the asymmetric simple exclusion process, I will consider it on the cycle graph, and I will imagine that there are, I'll give myself M, which is less than N particles, and the graph is of length M. And the transitions will be going clockwise. So 1, 0, whenever a particle is followed by a vacancy, the particle can move clockwise with rate 1. And if the particle is preceded by a vacancy, it will move there with rate Q, where Q you think of as a parameter. It makes sense to have Q less than 1, less than or equal to 1, but it's not important. So here's how you write down the Markov matrix. You write down your configurations in some order. So I've written it in Lex order. And as I said, this is a column stochastic matrix. So for example, this Q here is the probability of going from this state to this state, the second state to the first state. And sorry, the other way around. Going from the first state to the second state. Maybe I'll not use the highlighter. So it's this. And it goes with rate Q because this one over here moves left. Okay. So all the entries are all the off-diagonal entries are filled out this way, and the diagonal entries are filled so that the column sum is 0. And what we have to do now is to find the column vector with eigenvalue 0. And in this case, this is particularly easy because you notice that row sums are also 0. Somehow it turns out in this case. Okay. And so you can take V to be the all ones vector. And so your stationary distribution is the same for all states. So this is a bit surprising if you have not seen this before, because this is independent of Q. Okay. And you know, even physically, it might seem strange that, you know, configurations where all the particles are bunched together has the same probability as when they are spread out and in any way. So this is a general result, and this is folklore, that the stationary distribution is always. Okay. So so there's a class of models which are integrable in a certain sense. So maybe since I'm running low on time, I don't want to get into all the details. But the point is that integrable models satisfy something called the algebraic, called the Yang-Baxter equation, and using a machinery called the algebraic Bethe-Ansatz, one can determine the eigenvalues of the Markov matrix. And when there's integrability, one can also introduce disorder. But these disorder parameters will not be physical in most cases. But in very special cases,
which means what in practice? What's the non-physicality?
Well, the transitions, you know, the transitions will not be how should I put it? I mean, there will be cases where particles will move, for example, far away, or when this moves here, something else will do some other jump over there or so on. You know, so it won't be terribly physical. I mean, of course, there's nothing forbidding you from defining it that way, but it's usually not physical. However, in special cases, even these parameters lead to a physically reasonable model. And these are what I think of as combinatorial interacting particle systems. So for me, the Venn diagram is very simple. There's all interacting particle systems. They are the integrable ones, and which are nice in a sense. And there are the combinatorial ones, which are even nicer. So we want to focus on those. Okay, so let me give you some examples. So the example that most of you might have seen is the Zeppelin library, where you think of n books living on a shelf, all distinct, and each arrangement is therefore a permutation. So for example, here's an arrangement of books. So the graph is a path graph. It has closed boundaries, meaning nothing can enter or leave. And the probability of choosing book BI is xi. And once a book is chosen, so for example, you think it's a library, once a book is chosen, it's taken and moved to the right. And the other books are shifted. So it's, from the permutation point of view, it's the action of a cycle. Okay. And Zeppelin, this is the famous Gilfan Zeppelin. And Hendricks, in a 3-page paper, independently, proved that the stationary distribution of any arrangement B of this library has this beautiful formula. So it's the product of xbi divided by x of b1 plus up to x of bi. Okay. And I want you to appreciate that it's not even obvious that this is a probability. In other words, if I sum over all permutations of pi b, I get 1. So to say what the partition function is, I have to take the common denominator of these guys. So for every subset of 1 through n, let xs be the sum of xi's for I in S. Then the partition function is the product of all xs's, all non-empty subsets of 1 through n. So you notice that this is manifestly a symmetric function in x1 up through xn. So this is what I mean by combinatorial interacting particles. And for not obvious reasons, you get the partition function to be completely symmetric. And there are many generalizations, and one of the advantages of an online talk is that you can sort of go back in time. So Stuart Margolis gave a talk where he explained how these models can be interpreted using left regular bands and so on. Okay, so right. So another example is the totally asymmetric zero range process. So here we're looking at the cycle graph, again, m particles. Now, as I said, each site can have arbitrarily many particles. So suppose the ith site has more than one particle, let's say A. Then the one particle from there moves right with rate 1 by xi. Okay. And so it has one less particle and the neighboring site as well.
Sorry, what's xi?
Xi's are symbolic variables. X1 well, through,
it doesn't depend on A though, right? So
no.
So in this model, it doesn't matter. Doesn't matter how many particles you have at the site. The rate is the same. Okay.
Yeah. Yes, this is a too simple zero range process. Yes, exactly. So this was already shown by Spitzer in his first work, that the stationary probability of a configuration is the product of xi to the eta I, where eta I is the number of particles at site I in configuration eta. And the denominator, which is the partition function, just turns out to be the complete symmetric polynomial, which is again symmetric. And whereas you a priori would not have any reason to expect. Okay, so there are more models. So there's ASAP with annihilation. There's something called an asymmetric Glauber model. So there are many models where you have partition functions which have nice symmetries, even though the underlying graph doesn't have that symmetry. Okay, and this is what I want to advertise as kind of combinatorial models. So in this, okay, so I don't want to say much about it, right? Okay, so I want to focus on the long-range exclusion process. So let me talk about this. It's the simplest version, or one of the simplest versions. So now let's consider the path graph with open boundaries. So when I say open boundaries, particles will be allowed to enter and leave. And there'll be at most one particle per site. Here, because it's long range, the transitions will be non-local. And they're as follows. So suppose, so you imagine that there is there's a particle over here on the left boundary, separated by the system. So with rate alpha 0, it will try to enter and it will look for the first available site that it finds. So it can't go here, it can't go at site 1, it can't go up to some site, let's say I. So it will go to the first available site, which in this case is I+1, and you get this configuration. Okay. If the first site were empty, it would just go there. Now, suppose there is a particle at site I, then it will move right and find the first available site J, which is vacant, and it will go sit there. Okay, so this is the transition with rate alpha. And it is possible that you had a particle at site I, and all the sites to its right were occupied. In that case, it just exits the system. So you imagine that there is a vacancy somewhere here at the end, and it will just consider. Okay, and this is also called the push ASAP, because you think that this particle pushes this, which pushes this, and so on, and all of them push one, which is sort of the same thing.
At each, this is discrete time, right?
No, this is continuous. So these are all rates.
It's rates, I see. And it's the same thing is happening at each site.
That's right.
At the same time, they're all deciding whether to move or not. Okay.
Exactly. And because of general nonsense, you know that at every time there'll be only one particle, at most one particle that moves. Right. So this is also called the push ASAP, as I said, and it is isomorphic to something called the Hammersley-All, the diaconus process, where the role of the ones and zeros is interchanged. That is a little more general. That works even on R, but you can have a version on Z. Okay, so here the stationary probability of this process was studied with Anna Schilling's, Ben Steinberg, and Nicolas Thierry, and later in a separate work by myself. The stationary distribution is a product measure. So with density alpha naught divided by alpha naught plus alpha I at site I. So somehow, so therefore the partition function is the product of alpha naught plus alpha I, which is again symmetric in the alpha i's, where I goes from 1 to n.
Basically, so again, this is a statement of independence. The different sites sort of don't care about each other.
Right, exactly.
Okay.
Exactly. So somehow it's a miracle. I mean, it's not something that you would expect from the transitions. Yes, exactly. Okay, there are many other examples, and some things that I have studied with my collaborators, random juggling processes, and recently with Philippe Nadeau, we studied a two-dimensional exclusion process where again, for certain parameters, we get symmetric functions. This was accepted just last week in the European Journal of Combinatorics. Okay, so I'm about halfway there. No, not really, but whatever. So I want to now focus on this multi-species version of the totally asymmetric long-range exclusion process. So, so here the graph is Cn. Each site has exactly one particle of some species. So now there are many species of particles, and there are mi particles of species I, so that n is the sum of these guys. And we think of 1 being the strongest particle, it's called the first class particle, 2 being the next strongest, that is the second class particle, and so on. And you can think of S as vacancies, if you like. It's the weakest particle. So let me describe the transitions. So suppose you have so at site I, suppose you have a particle, and the exponential clock at site I rings with rate alpha I. When it rings, the particle at site I moves clockwise. It finds the weakest available particle. So just like in the simple long range exclusion process, and it displaces it. Now that particle which got displaced will in turn do the same. It will go and find the next weakest particle to displace it, and so on, until you end at particle S. At some point you have to, that's the lowest. And that will go and jump to I.
And it's all considered to be happening at the same time, yes?
Yes. So all
more or less
happen simultaneously. Right? And we call this the M tal rep. And a homogeneous version was studied by Ferrari and Markow. So just to give an example, so with rate alpha, so consider this configuration. With rate alpha 2, the 1 will jump to the 2. We will find the first available particle, which is the 2. This will jump and find the first available particle, which happens to be the 5, which is also S. So 1 will move to the 2, 2 will move to the 5, 5 will move to the 1. So that's what happens here. If it rings at 5, nothing happens. If it rings at the site 5, which contains the 3, then the 3 looks and finds the first larger particle, which is the 4. 4 goes, remember this is on a cycle, so it will go and come on the other side and find the 5. So 3 will replace the 4, will replace the 5, will replace the 2. Okay, that's the idea. So the basic, one can show that this process is irreducible, and it's also invariant under simultaneous translation. That is, you change the label of the sites from I to I+1, and also you change the parameters alpha I to alpha I+1. It's like covariance. So here's our theorem. Jointly with Gidi Amir, Omar Angel, and James Martin. So you have these species, this tuple label you how many species of each kind there are. Then the stationary distribution is given by some polynomial in the alpha 1 with integer coefficients of alpha 1 to alpha n, such that the GCD of all these guys is 1. And if you let capital Mi be small mi plus 1 up to ns, then the partition function is the product of the elementary symmetric functions indexed by mi in the variables alpha 1 to alpha n. So let me give you an example. Oh, before that, let me state a connection to the multi-species space set, which has been of interest for some time. So again, if you have the same content, the multi-species space set says that 2 adjacent sites switch if the left side has smaller value than the right side with rate 1. This happens with rate 1. Okay. And in a beautiful paper in 2007, Pablo Ferrari and James Martin proved that the partition function of this model is the product of these binomial coefficients, and choose M1 plus M2. In particular, if all the MIs are 1, this is the product of the entries in the Pascal's, in one row of the Pascal's line. Okay, it's the product of the entry. So it turns out that if you set all the alpha i's to be 1 in the M-tal rep, you get the same partition function because the EIs will reduce to this. And the proof used a so-called multi-line process that we will modify. So let me give an example. So let's look at some transition. So let's say, let's look at this alpha 1 over here. This is the transition 1, 3, 2. So here the 1 goes to the 3 and then the 3 goes to the 1. So, so that's why you are in the 5th row. Okay. So second column, 5th row. That's this. Oops, sorry. Okay. And in this case, the stationary weights turn out to be given by this vector. And the partition function turns out to be the product of alpha 1 plus alpha 2 plus alpha 3, that is E1 times E2. Okay, so
in general, the stationary weights are not only polynomials in the alpha, but also polynomials in the M, right? In the entries of M, the number of occurrences of each type of particle.
Yes, that was the Markov chain tree theorem. Exactly. Yes, exactly. Okay, so since I'm running out of time, maybe I will not go into the proof strategy. I should say it follows more or less the strategy of the proof of Ferrari and Martin. We define. Okay, so maybe this is important, so I will spend some time on it. So we will look at a Markov chain, a larger Markov chain, which will project to this M-tal rep. Okay, and that's so let me describe that. So remember, we have this tuple indexing the content. So think of a discrete cylinder with height s-1 and circumference n. And you think of each side being either vacant or occupied by a particle, such that the ith row has m1 plus up to mi particles. Okay, I'll give an example in a moment. And you let omega hat be the space of all such configurations. So then what we call the multi-line tal rep is the process where with rate alpha I, the bottom side rings at I. Okay, maybe I'll explain with this example. So suppose, so with rate alpha I, the clock here will ring. This particle will try to move like the tal rep. So it will try to find the first location, first available location. So it will go there. Now, wherever it moves, you look up. You go one step up, one row up, and see if there's a particle there or not. And if there is no particle, you move further up until you find a particle. And then that particle will do the same. So it will find the first available, it will move and find the first available site. In this case, it's just the neighboring site. Then you go up again to the next row and so on. And this will find the next available site. So at the end of the day, you have this configuration will transition to this configuration. Everything else remains the same. So this is called the multi-line tal rep. And again, we show that it's irreducible and it has the same symmetry property. And the stationary distribution now is for this is given as follows. So if you let Cj of eta be the number of zeros in the jth column of eta, then the stationary distribution of eta hat, sorry, a configuration in omega hat, then the stationary probability of eta hat is the product of alpha I to the Ci of eta. Okay, and this will show immediately that the partition function is what we have. Piotr, how am I doing with time?
You have about 10 minutes.
Okay, thanks. Okay, so here's the example. So this configuration has weight alpha 1 squared because there are two zeros here, alpha 2 squared, alpha 3 cubed, and so on, alpha 4 squared, etc. So you get the idea. So this will be the stationary distribution. So it has the property of being of product form. And so each row, what happens in each row is independent of what happens in any other. And as I said, the strategy of proof is to follow strategy of Ferrari and Martin. Okay, so I'm running out of time, so I won't explain this key combinatorial lemma, but let me explain how the projection works. So this is a Markov chain on an enriched, on a larger space, and this will project onto the M-tal rep, and the projection will go as follows. So at the first step, so what I'm going to do is I'm going to take a multi-line configuration, and I'm going to give you a multi-species configuration in one row. And the way it goes is the following. So first you start with the particles on the top row. Each particle will trace a path, start going below, immediately below, and going right until it finds a particle and repeating. So this particle will go down, find the next particle, the nearest available particle, after which it will go down and find the nearest available particle, and so on. And it will end at the bottom, and all of these will be called ones. Similarly, here, this one starts here, and it comes here in this row, and then the next row it goes over here, and the next row it cycles and comes over here. Okay. It turns out that the order of choosing particles in any given row does not matter. So next you have some particles which are not yet labeled in the second row, in this case only one, so that you repeat that process. It goes down, finds the first available particle which has not yet been taken. This one has already been taken, so it goes here, finds this 2, comes down, this one has already been taken, 2, 2. And then you do it with the 3s and the 4s and the 5s. And at the end, you end up with this configuration 1, 2, 5, 3, 3, 1, 4, 4, 5. That is the projection. So this is the projection map from this multi-line process to the multi-species process. And one needs a proof, but it is true that this is a valid projection, in the sense that you get the multi-species process when you restrict the multi-line process this way. Okay, so if I go back to the 1-1-1 example, oh, I cannot click here. Okay. All right. Anyway, so if you look at the configuration 3-1-2, then there are 2 configurations that project to it, this and this, and they have weights alpha 1 squared alpha 3 and alpha 1 alpha 2 alpha 3, and if you sum them, you get the stationary weight of 3-1-2. And similarly for 3-2-1, you have only 1, and that will give you weight alpha 1 squared. Okay. All right. So right. So now let me talk about the refined version of, generalized version of this, where the McDonald polynomials will enter. And the way this works is that instead of, okay, so let me define the process directly. So recall that we have the t version of an integer. Usually one uses q, but here q is reserved for something else in McDonald world. So we are using t. So now we have these transitions which are similar to the M-tal rep. So whenever a bell rings at site I with rate alpha I, the particle at site I moves to the right. It will replace, so now earlier it replaced the first available weaker particle, right? But now there is this possibility of rejection. So it will choose the jth available weaker particle with probability t to the j minus 1 proportional to t to the j minus 1. Okay, that's the idea. So I'll give an example in a second. And then the displaced particle does the same. And we continue this way until you end at the particle of species S, and you jump back. Okay, and this we will call the M-tal rep with rejection. So here is an example. So the bell rings at the third site. So this 2 takes off, it could go to the 5, but it rejects it. Then it could go to the 3, well, it rejects that also. It could go to this 4, it rejects that also. And it goes to the last one, which is 3. And that is proportional to t cubed, because you have t to the 0, 1, 2, and 3. So that's t cubed divided by 1 plus t squared plus t cubed, which is 4t. Now, once it replaces, the 2 replaces the 3 then takes off. It could have replaced the 5, but it doesn't. It goes to the 4, and that happens with probability t by 1 plus t. Then the 4 takes off. It doesn't have a choice. There's only one 5 available, one weaker particle, which is the 5. It goes there. And now at the end, the 5 goes back to the 2. So as was asked, all this happens instantaneously, and this happens with this rate. The alpha cubed is because this transition started at the third side. And what we prove is that the stationary distribution is again proportional to some polynomial with integer coefficients of alpha 1 to alpha n and t. And the denominator, which is the partition function, has the same elementary symmetric function product as before, and a product of ratios of t factorials. So somehow the t has not influenced the partition function. It is there in the stationary distribution. It has not vanished. But when you sum all of them, they neatly separate. The t part is separate from the non-t part, or the alpha I part, if you like. And the proof strategy is completely indirect, and we use a result of Cortell, Mandelstam, and Williams, where they gave a combinatorial formula for the permuted basement Macdonald polynomials. And we use a result of Alexanderson and Sony, where they proved a certain factorization property. This should be q equal to 1 for the permuted basement Macdonald polynomials at q equal to 1, which gives our result. Okay, so somehow this we have a very indirect proof, which we would like to understand. So here is for the same model, here is the stationary weights. You can see that each weight depends on t. But when you sum all of these, this miraculously, the t part comes out. And this elementary symmetric functions were the same. So those of you who were lured by my title and abstract and were waiting to hear Macdonald polynomials, here they come in the last couple of minutes. So we believe that this is really a version of the Macdonald polynomial with q equal to 1. And that is because the Macdonald polynomials at q equal to 1 specialize to the product of elementary symmetric functions. And so that's, and there are some more reasons which I'm not getting into for lack of time. I was also going to talk about the M-taser, but as I fully expected, I ran out of time. And so you please see the poster by Olya Mandelstam next week, which is joint work with James Martin and myself. And so I'm almost out of time, right, Piotr? Okay.
That's right.
So let me not talk about any of this. And I will just advertise FPSAC 2022, where we have a very exciting list of speakers, including the current chair of this session, coincidentally, I think. And I hope to see all of you in Bangalore then. And hopefully by that time, this third wave would have gone, this nth wave would have gone down, and the n+1th wave would not have taken off. And I thank you all for your attention.
Thank you very much.